Hello, my name is Antonio Iverdi, and today we're going to be talking about Lab 3, which deals with the magnetic field of a bar magnet. The purpose of this lab was to measure the distance dependence of the magnetic field due to a bar magnet. We're going to be using the Biot-Savart law to create a computational model to visually represent the magnetic field of the bar magnet for on-axis, perpendicular, and off-axis observation locations. Then we compared experimental values with values derived from the computational model. As you can see, the results here was that the calculated value for distance dependence was n equals negative 3.5502, while the theoretical value used was n equals negative 3, as given from the edX video. We also then have listed our predicted value for the magnetic field 45 degrees off axis, and then we have our observed value for the magnetic field 45 degrees off axis. Some fundamental physics principles being used here. We know that the magnitude of the magnetic field decreases as the observation location moves farther away. You can see that from this equation. We know that the Earth produces a magnetic field of its own, and we will be utilizing the Biot-Savart law, which gives the magnetic field of the dipole formula. To begin this lab, we have to compensate for the magnetic north pole. So we oriented the phone to make the x component of the magnetic mirror 0, and then my location used for this lab was Atlanta, Georgia, and the net magnetic field here was 49. Now we had to locate the magnetometer chip. The bar magnet was first oriented along the east-west axis. Then the phone was slid along a line perpendicular to the meter stick until the x component was at its max, the y component was at its min, and it was then marked with tape. Then the phone was rotated 90 degrees, once again slid phone perpendicular to the tape until the x component is maximized, the y component is minimized, and then that is marked with tape. Finally, you can find the magnetometer chip, which is located at the corner of these two intersecting tapes. Listed here are my measurements and observations on axis, and as we can see from the values, as the magnetometer is moved closer to the magnet, the x component of the magnetic field increases. When far away from the magnet, the x component of a magnetic field is nearly 0. Listed here we have my measurements for the off-axis. And as you can see from the diagram here, it kind of shows the setup for this for these measurements. And the experimental B at 45 degrees to be found from this was negative 8.22 times 10 to the negative 6 and negative 2.32 times 10 to the negative 5th. Now we have the calculation of n. And the equation here is the equation that was used here to plot these points. And as you can see, since the n from the negative slope here, since the magnetic field is decreasing as the distance is decreasing, and the slope being used here would be expected to be negative. As you can see from the graph, we get a line with a negative slope, and the slope is given by n. So our n was found to be negative 3.5502. Now we have our magnetic moment calculation. We're using the equations both from the fundamental physics principles listed before and the equation used to graph that line. Then you can kind of solve for ln of k, because that's going to be your y-intercept. And then from there you can solve for k by doing some algebra. And then with more algebra you can finally solve for mu. And then our mu is found to be 1.875 am squared. Now I have my glossary calculations here for the computational model. First, we use that magnetic moment just calculated and added into the code in line 24. Then you can go to the right of the screen. We have the creation of the function for the magnetic field in lines 33 through 36. And then we have our creation of observation locations in lines 56 through 61. And then we create arrows to represent both our magnetic fields on axis and magnetic fields perpendicular to the axis. Then we have to add in the average perpendicular distance, which was in line 109, and that is given from our Excel sheet. And then we have to add in the arrow representing the magnetic field 45 degrees from the axis in lines 119 and 121. Listed to the right is my computational model itself. As you can see, the blue arrows represent perpendicular observation locations. The orange arrows represent magnetic field added on-axis locations. And then finally, the purple arrow all the way to off, it represents the off-axis location, or B at 45 degrees. And listed below, you can see that value for the magnetic field at 45 degrees at distance d. So here are the two values of B at 45 degrees. So our predicted value, which we got from the computational model, which was listed right under the diagram, was found to be 2.56 times 10 to the negative 6, and then 7.69 times 10 to the negative 6t. And by adding the square of each one and then taking the square root, we can find the B net, which is found to be 8.11 times 10 to the negative 6t. Finally, we have then we compare this to our observed value from our measurements of the Excel sheet. And that was negative 8.22 times 10 to the negative 6, and then negative 2.32 times 10 to the negative 5t. And then the B net is also listed from the Excel sheet, and that was found to be 6.48 times 10 to the negative 5. Now, this value is, the discrepancy here is definitely because of minor human error and the calibration issues from setting up the meter stick and everything. It wouldn't be completely accurate. In conclusions, if the magnetic north was not compensated for, the graph function would still look the same because the results would have shifted by the same magnitude, but there would be an even larger margin of error in the lab, an even bigger discrepancy. And finally, if we were to stick two identical magnets together end to end and run the experiment again, the magnetic field at each location would have doubled. The magnetic fields would not cancel out, they would add together.